So our talk here is pretty much inspired by what we've all heard today a couple times, which is, when we build an actual real chatbot, usually we don't have like terabytes of data to train the dialogue manager. So we do need to come up with an approach to be smarter than just a scripted system. So today we're going to be talking about how exactly this can be achieved in a commercial setting. All right? But before we begin, some fun. Now, imagine a question like this. How would you actually prefer to order if you have an order like this? Medium extra hot latte macchiato with skimmed milk and a double shot of espresso. Like this, which is nice and natural, or like that. So, choice number one, probably you're human, right? So this is like the basic premise that we're building upon. So we are saying that we as humans basically prefer to express what we want through our natural language in general. So it not necessarily is going to be a language as a text. It also can be interaction based on images, interaction based on smart types of content, and so on. But hey, during the industrial age, we've all got too much, basically cornered with the existing interfaces, so we had to really learn how it all works. So we learned interfaces for washing machines, coffee machines, and everything else like that. But now we think it's time to get back. So now it's time to make machines think and make sure that they can now start learning our behavior and start being able to deliver what we want instead of us trying to decipher their interfaces. Right? Agreed? Awesome. So that's how we ended up with what we call conversational commerce. Basically, something that can be seen as the continuation of the chatbot's paradigm in general. So we see it as this, a brand being able to have a hyper-relevant one-to-one personal, goal-oriented conversation on any channel with any customer at any given point in time. Right? So how is this different from a common chatbot, from what we all heard about many times? Well, in many different respects, but above all, of course, what we are building here is based on integrations and delivers multimodal output to different channels. But what we think is exceptionally important is this part. So being able to handle exceptions and enable continuous learning based on failed conversations, because we have way too many of those. So that's how we arrived to what we call the end-to-end learnability. And Kostya here is going to have a deeper talk with you about that. So buckle up.
So, okay, we are talking goal-based architecture here, which is a system where we have a collection of predefined scripts which users have to follow in order to achieve their goals. And that kind of architecture has their benefit because we can actually use those scripts to make people achieve their goals with the dialogue. But that's not the kind of things that we can really train. And we have to invest a lot of into creating those scripts. The problem with them, though, is that they're very brittle, and people really have to know how to talk to that systems. They have to follow the rules so that the system can help them achieve their goals. And that's very much different from what people usually do when they talk to each other, because when people talk to each other, we expect different things from the system, and that leads to really breaking the script, and the result is that those scripts don't really work that well. So the usual pattern that we can observe when dealing with those types of technology is that the usual pattern that people follow is they always seem to try to test the limits of that system. They always try to break it. So once users understand that they can't really achieve their goals, they understand that they are not dealing with a real person, but instead they're dealing with a toy, and the childish attempt is to break it. So in order to mitigate the problem, we kind of try to turn things around, and instead of dealing with the usual goal-oriented system, we want to think of that in other terms. So we want to say that the real intent that people have is to break the toy. And we decide to think that the main goal of the user is to break the system, and to do that they employ a number of strategies. Those strategies can be the following. So for instance, if you have a dialogue which is, so on the left, the dialogue that is obviously broken, this is because the system doesn't seem to be able to use its memory, so the user would expect the system to remember stuff and then to retrieve that as needed. But instead, we see that it does not succeed in doing this. So when we turn those things around, we say that the user's intent is to demonstrate that the system is broken, and to demonstrate that the user employs a strategy of showing that the system is forgetful, so that it does not use its memory properly. On the right, there's another example of a broken dialogue where the system should be able to spot the contradiction, but it can't do that. So in order to find and spot those places in the dialogues, we want to have a collection of bad intents. And that is a bad intent detection. So we can define a number of strategies that users employ to break those toys. And they can be like targeted at building an approach where the system is not capable of interpreting the information in a correct way, or it may confuse words and entities, or it may not understand the language completely, may not spot the wordplay, or it may be forced to repeat itself multiple times. And that all those cases would be considered to be the failed dialogue. But that's a problematic point here, because people usually employ some other strategies that are perfectly normal from the standpoint of the usual way of communicating with other peoples, like the fatigue function. So the fatigue function is the expressions that people use that do not relate directly to the usual goal of the dialogue, but their main purpose is to keep the emotional connection with each other. So it might seem like being irrelevant, but on the other level, it's irrelevant. It's relevant to the dialogue because it helps people understand that they have an emotional connection. And so we want to add to those intents things like those. And we also want to know when people cooperate in order to continue working with the script and follow the strategy that was put into the dialogue by its creator. One of the assumptions that make it possible to implement is the assumption that we should not allow the system to relate to some information that is not contained in the previous dialogue history. So, for instance, if we're talking goal-oriented dialogue, then, for instance, if that's ordering a pizza, then general knowledge questions are not allowed there. So we do not expect from a person to ask what's the radius of Earth if the person is ordering a pizza. And so, although for some applications there would be a normal question, for that application we think that it is an attempt to break the toy. And now, building on this assumption, we can actually make a model of the dialogue, which is a model that we can actually train and implement. And it turns out that in the history of computational linguistics and logic, there was a number of proposals that are well suited to this task. So here's some pretty old history. when we think about the structure of a dialogue, it might be represented as a tree, like a syntactic parsing tree. And these similar kinds of structures appear in logic. This is one of the ways of representing proofs which build on assumptions that are made. And so applying some rules in that system discharges the premises that were made earlier. And then if we follow the rules of the game and if we arrive at the final conclusion by discharging all the premises that were made, then that's a proof. The problem with that type of representation is that it is too complex. It's too complex. It's a structured representation that is really hard to train. So we want to internalize the context. And there's another approach in logic which allows to do that, and that's called a sequence-based calculus or a sequence calculus. And those are expressions that keep the context with itself. Now, the problem with those types of logics is that they are not really suitable to modeling the natural language. In natural language, we have some properties. Like if we use a resource, we may not use that for the second time, or if we may not reorder things. So if that's a dialogue, then we may not switch to sentences because that would really change the meaning of the dialogue. And so the logic that we employ here is another type of logic, which is non-classical, and this was proposed in the late 50s by Lambda. And this is a Lambda Calculus, which is based on the notion of syntactic categories. The category is a thing that represents classes of context, and the way the logic builds is by gluing those contexts in a coherent whole. So here's another example of rule application in Lambda Calculus. We can view those things in two different ways. One way is those categories represent the context, and the other way, they represent functions that consume resources and produce some other resources. And here's how this is modeled in the original system. So we want to phrase the problem of proving that something is a valid sentence given a lexicon, and the inference should be a valid inference for that to count as a sentence. So here you see a sentence, John loves Mary. On the top there's a lexicon, so this is an assignment of syntactic categories to words. And if we are able to prove that this sequence reduces to a special symbol S, then that's a sentence, that's a proof. The next thing to do is, all those theory behind that is not really trainable, so we want to make that, to convert that into a system which we can use, which we can learn and train based on data that we have at our disposal. So to do that, we want to somehow relate that system to the approaches that are known currently in the machine learning community. And the key insight here is that it is possible to represent proofs in different forms. One form might be the tree that you've seen earlier, but that is also possible to represent that in a different form, which is proposed for that type of logics, the resource logic, and that was called a proof net. So a proof net, building the proof net, starts from decomposing those syntactic categories into smaller parts, and that's the way to do that. To do this, these are 3 examples, and the last one is exactly the syntactic category. This is decomposed into the atomic categories with polarities. The next thing is that we can build a sequence of those syntactic categories and then apply that procedure of decomposition to arrive to a sequence of atomic categories with certain polarities. And then the next thing, to complete the proof, what we have to do is we have to build a linkage for that frame. So the simple interpretation for that is the following. So in a sentence, people provide some resources, some facts, or some information that should be linked to some other information in some other sentences. And if we are possible, so in some sentences provide resources, other sentences require resources. If we are able to connect them in a coherent whole, then that's a proof. And as you might see, what we do here is actually a sequence-to-sequence modeling. So this is a translation of one sequence into another sequence, which is actually achievable with the current deep learning architectures like seq-to-seq models. And the linkage here is the kind of thing that can be achieved with attention models. There's a running joke in the NLP community currently that if you want to solve just about any problem in NLP, you just take LSTMs with attention. And that's kind of exactly the same, the exact thing that we do here is that we model that problem of converting one sequence to another sequence and then applying attention to complete the proof, to complete the linkage. Now, in those methods, in the tasks that employ those methods, we can translate between modalities. So in the simplest case, which is the main application for that types of models, this is neural machine translation. So we take sequences of tokens in one language and we produce sequences in another language. This is machine translation. But we can also translate from different modalities. So we can take as input images and we can produce captions to those images. And here, what we do here is we take dialogues and we convert them into proofs that they are broken. So the correspondences that appear here is that we can treat syntactic categories as embeddings, the sequence of logic as sequences of atomic category, of sequences like in the seq-to-seq models. The sequence decomposition becomes the translation with the seq-to-seq model, and the linkage is achieved with an attention. And on the left, you see a matching or an alignment between the complex syntactic categories and the atomic categories, which is the usual picture in the attention literature. Now, how we can use that, since we want to use that as a component in a goal-based system, we think of that as a special component which evaluates the proposed hypothesis from the main rule-based or goal-based system, which can then be evaluated for whether that particular answer will break the flow of the dialogue or not. And if that's possible, so if the response that we are evaluating breaks the dialogue, then we would probably take some measures to avoid that. And so if we apply that during the dialogue by rescoring or re-evaluating the proposed answers from the system, we can make it more resilient to problems. So there are a number of ways how this method can be used in the traditional goal-oriented system. We can either feed the system with the scores from that component, or we can directly use that information by the agents that produce the responses, or we can employ things like reinforcement learning to make the future dialogues better, or we can generate a set of hypotheses and rescore them to find the best answer that will most likely not break the dialogue flow.
And that's pretty much it.
So this is a way of making the traditional systems more resilient. And this is a sort of a hybrid approach which combines the traditional goal-oriented systems with methods which can be learned and trained from data. And that really is something that can be deployed as a component in the running systems. So the running systems will not be replaced completely, but we can augment them almost seamlessly and just benefit from that technology. So thank you.